Yes, Harni.
Okay. So, almost afternoon. Good afternoon to everybody. Glad to speak with you all again today. I'm here to just give you a quick 5 to 10 minutes introduction to what we'll be doing in the first 1 hour of the afternoon lab session at 2:30. So, in the morning session, we saw the decision tree, and Sir explained the decision tree algorithm and also different performance metrics like precision, recall, etc. So, for the lab session, what we'll be doing is we'll be using the decision tree for a classification problem on this data set for drug prediction. So, what is this drug prediction problem? So, we have some patient records. So, we have some information available about a patient. Okay. And we also have which drug out of these five was recommended to that patient. So actually, by the way, this notebook, a Python notebook, will be shared to you after this. So you'll be using this in the afternoon. So just to give you an idea of how the data set looks. So you can see these are just 5 records out of the 200 records which will be giving you the data set. So you can see that there are 5 attributes or features, as we call it, about a patient. So we have the age of the patient, the sex of the patient, blood pressure level, whether it's high, low, etc. The cholesterol level, the sodium to potassium, and also level, and also which drug was recommended. So for patient 0, this drug Y has been recommended, and for patient 3, drug X has been recommended, and so on. So we'll be using the decision tree algorithm to predict which drug to recommend for a new patient record. So that's what we'll be doing. And we'll also be applying another simple algorithm called K nearest neighbors. So during the session, I'll also give you a quick brief on what this algorithm is. And so we'll be using the scikit-learn library for the decision tree classifier implementation and also for the K nearest neighbors one. So if you recall yesterday during the neural network session also, we had used the scikit-learn library for getting the multi-layer perceptron implementation. So it's a very useful library to get these direct implementations. So we don't have to encode any of the algorithm, so on. It's directly available to us through this library. And NumPy and Pandas, again, you would have been familiar with it by now. We use them extensively for these for handling data, in arrays and matrices, and even matplotlib. So you would have used them to plot, graphs. We'll use matplotlib here to visualize our decision tree. So similar to what Sir had shown a diagram in the session today. So it will look something like this. So yeah, and after that, we'll be also looking into the metrics. So after running the decision tree classifier, we'll print out what is the precision recall to see how well it is performing in the data set. So so that's a quick introduction for you. So hope to see you all at 2:30 p.m. today. So I guess the next session can start, and I'll come back at 2:30. Santosh sir?
Yeah,
Yes,
Harni.
I am done. That's
Okay.
just introduction. I'll come back at 2:30 for the first 1 hour of the lab session.
Okay, fine.
And this file, this Python notebook, along with the data set file, we can share it with them, sir, in the afternoon break.
Yeah, like once you come into the session, we can drop in the chat, and as well as we'll keep it in WhatsApp group also, links and everything.
Sure, sir. I'll send this notebook file.
Okay, you just send links to me also, to my mail.
Okay, sir, sure.
Yeah. And now I hand over the session to Akash, Mukesh, and Dani Prakash.
Yes, sir. I'll take over just a minute.
Sir?
Yes, sir. I'll take over. I'll share my screen. Just give me a couple of minutes.
Yeah, I'm sharing the links for the resources that we have used in the chat window, so you can use them.
Okay, yeah.
That can be copy pasted to whatever other means of communication.
Yeah, I'll do that.
Okay, can I guess see my screen?
Yes, Akash.
Okay, the presentation slide is visible, right?
Yeah, we can see the presentation slide.
Oh, okay, then we'll go ahead and start the session. Okay, very good morning to everyone present here. Myself, Akash, along with Mr. Mukesh and Dani Prakash, will be teaching you the basics of natural language processing and text analytics. So, let's see, to start off, we need to know what is natural language processing. For that, like, we first need to understand the concept of natural language. So, we as human beings have communicated and shared information primarily in the form of text and speech. So the years we call this information which we share as a form of text and speech as natural language, and we can say that it's one of the most diverse and complex part of us, considering there are more than 6,500 natural languages. And if you look around you in your day-to-day activities, you'll be surrounded with text and messages. You keep interacting with menus, emails, web pages, SMS, and whatnot. So the primary means of communication and information sharing is through natural language. Now, now that we know what natural language is, we need to know what NLP processing stands for. It is basically a branch of artificial intelligence wherein we use artificial intelligence to communicate with an intelligent system using natural language. So the ultimate goal is to help computers understand our language as well as we do. So since in whatever domain we take, the primary means of communication is either through text or speech. There is a lot of scope to leverage the power of NLP. And let's see a few applications one by one. Quickly glance over the application before we go through the technical aspects. So yeah, conversational agents. So we have been seeing NLP-powered software such as Google Assistant, Siri, and Alexa, which can hold a speech with us, take the input speech from us, and analyze the language. It processes our dialogue and extracts the information from it, converts the resultant query, result of the query from the extracted information into back to speech and converses with it. So there's a lot of scope for such conversational agents which use dialogue systems powered by NLP. Then there's sentiment analysis. So we know that in social media and other platforms, we tend to see user reviews. They basically engage with the platform and represent their views on the product through reviews and comments. So businesses want to know how they can understand the emotions and opinion of the users. So basically NLP and statistics can be used to assign values to text such as positive, negative, or neutral, and also identify the underlying mood of the context with which he has written, whether he was happy, sad, or angry. Then question answering systems. So in we have seen that when we search Google for a question directly, it's able to understand, retrieve what kind of information and directly query the relevant result and provide us with a relevant answer instead of just redirecting the query to other websites. So basically what we do here is that automatically answer the questions and post the answer as in natural language rather than returning queries or whatnot. So we can also see that IBM Watson won the competition against humans for this particular task in the Jeopardy challenge in 2011. Okay, then yeah, of course. Then chatbots. We hear a lot of chatbots, which were preliminary solution for customer care assistance and all the simple low priority high turnover task, which just requires some little to no assistance from the business side. Intelligent chatbots now offer personalized assistance to customers. It's able to understand the intent of the conversation rather than just communicate and respond to the queries. Now we have seen machine translations as well. There's Google Translate, which automatically converts one form of natural language into another while preserving the underlying meaning. And even some social media platforms even have inline translate. For example, Facebook, if comments are there in some other language, there's an inline translate button which automatically translates it to the language of our choice. Then there's also text classification where you can automatically analyze the most of the uh, data or text available on the internet is largely unstructured. We can analyze these texts and then assign a set of categories, then categorize each text into those categories. Examples being spam detection and categorizing into labels in Gmail. And there are a lot more applications or day-to-day autocomplete features in Gmail. In while searching, if you just type "world," it gives you automated suggestion on autocomplete features. There's also spell checking and grammar checks. There's text summarization wherein you can summarize a single article or multiple articles from multiple sources into a summary. Then you can give natural language instruction to many smart devices where it understands the natural instruction processes it and responds accordingly, and speech recognition, so on and so forth. As you can see, there are lots of applications in almost any domain, since it's text and speech is what we use in any domain to get through for communicate information exchange or communication with clients. So there's a lot of scope to leverage the concepts of NLP. Okay, before we go into basics of NLP, you need to have a good knowledge of the language. So if you see on the basic level, we deal with phonetics and phonology, which is how the speech sounds, the sound of each word, how we pronounce it, and whatnot. Then on the next level is morphology and lexicons, which is basically individual words and their forms. Then we have syntax and its parsing, where we define the structure of a sentence. How a sentence is to be structured. Three determinants cannot be put together, and we can't call it a sentence. The, and cannot be just put together and call it a sentence. There needs to be a verb phrase, a noun phrase, noun further divided into determinants and verbs into adverbs, and so on and so forth. Then there is semantics, where we get the meaning behind the sentence and the purpose for that sentence. That's meaning for the sentence is semantics, purpose of the sentence and the context is pragmatics. Then there's also discourse, which connects multiple sentences together to form a large body of text using the same underlying context to be able to hold a prolonged conversation or to understand the larger scheme of things. Okay, next. So, okay, before heading into NLP, we need to know what are all the challenges which we face and what are all the challenges we need to resolve. As you can see, the main major challenge in NLP is the ambiguities that we face. As you know, like if you look at this example, there's a word sense ambiguity for the word lost, which can mean that his wife was passed away, or it can literally mean that the person is lost among the crowd. Then here, word sense along with the meaning ambiguity is present, wherein the assistant on calling an ambulance literally calls the person as an ambulance. And over here, there's proper noun attachment ambiguity. How do you perceive the statement to be? Did the San Jose cops kill a man using a knife, or did they kill a man who was holding a knife? So such ambiguities arise, and there are lots of them. Let's go through a few. So lexical ambiguities. So this primarily arises due to the presence of two or more meanings for a single word. It's also called semantic ambiguity or homonym. If you take words like bank, I went to the bank. The bank can mean the place where you deposit or withdraw cash, or it can mean a river bank. So that's there. And even here, I saw a bat. Saw can be either the machine saw or a past tense of the word see, and same way, bat can mean a mammal or a wooden bat. So such ambiguities where words have multiple meanings, it's called a single word has multiple meanings. It's called lexical ambiguity. So such ambiguity is often resolved in, like, we'll be seeing it in the basic tasks further on in the session, where it will be resolved using parts of speech tracking and name entity recognition. So next comes the language structural ambiguities, where the syntactic function cannot be uniquely determined from the meaning of the sentence immediately. So just from looking at the sentence, we can't immediately get the syntactic function of it, which basically means each of these sentences have multiple parse trees. The way you can parse it for more than one. So if you can see here, the man saw the boy with binoculars. Did the man see the boy using his binoculars, or did he see a boy who was having a binoculars? So as you can see, there are two ways of parsing this sentence. Then there's flying planes can be dangerous. This basically arises by having a verb plus ing, then a noun in front of it. This is another common way of giving rise to structural ambiguities. Now let's look at an example. Stolen paintings found by the tree. So for this, in this case, found is being the verb, which is being considered the agent of before the preposition, and it's being understood as the stolen paintings are being found by the tree. But if we further elaborate as stolen paintings found besides the tree, now it can properly determine that stolen paintings are the noun subjects and they are being found besides the tree. And yeah, ambiguity is not just structural alone and lexical alone. It can be pervasive, meaning it can be found in all parts. If you take this sentence, I made her duck, it can mean that I cooked duck for her, I cooked duck belonging to her, I created the duck that she owns, even I caused her to literally duck, the motion duck, I turned her into a duck. That can also mean. There are 5 different meanings for the same sentence, which arises due to multiple problems. Duck can either mean a noun or a verb, her can be possessive or dative pronoun. And if you want to go further in terms of phonetics also, if we can see that I'm 8 or duck is pronounced same way as I made her duck. And similarly for I'm 8 her duck. So now we might ask, why is our language so ambiguous? Why didn't we have all the rules in place before to avoid these ambiguities, just like formal programming languages? Well, we see in formal programming language, we have a deterministic structure. They can be defined by grammar and produce unique parts for each sentence. So why can't we do the same for our language? Well, our language primarily relies on our ability to use our knowledge and inferences from previous communications to properly resolve all these ambiguities. So we allow such ambiguities to permit shorter linguistic expressions in our language and also avoid the language being overly complex. So basically, we depend on our knowledge and inference abilities to resolve the ambiguities. Then those are just related to the ambiguities of the either semantic or syntactic. Now, there are other issues as well in the language, such as non-standard English. If you see tweets and whatnot, you'll have at the rate used to tag exclamation marks and then like hashtags and whatnot. So all these are to be passed together with the word, and that might be difficult. We need to extract the token as just the noun word over here, rather than including the punctuations. Then there will be segmentation issues where the New York Haven Railroad and the new where the hyphen is, where to add the hyphen. Is it between New and York, or is it between York and New Haven? And there's always idioms which we ourselves can't get the direct context. It's used to refer indirectly to a particular case, and there's neologisms wherein recent words are getting added, such as unfriend, retweet. We casually use the word Google it to go find out that information. Such kinds of words are constantly being added to the existing dictionary. Then there's world knowledge as well. Mary and Sue were sisters, and Mary and Sue were mothers, which is like facts which are supposed to be there. Then the key entity names. Where is a Bug's Life playing? Over here, a Bug's Life is a movie name. We can't interpret it the same way as in a normal sentence. So these are all the various issues we face in just the language part alone, which we need to resolve before going into processing. So apart from these issues, there's also these issues of scale, variety of what corpus you have chose. Different languages have different varieties, and some languages have word translation which others don't, and all those issues need to be taken care of. So, okay, before we proceed with basic tasks of NLP, let's look at basic terminologies. So, what is a corpus? Corpus is basically a collection of large and structured set of text for a language. There can be multiple corpuses, multiple languages put together called corpora. So they are basically we use corpuses for analysis and hypothesis testing. Like if you take the Oxford English corpus, it has over 2.1 billion words, which Oxford University Press research and its dictionary uses. Now, what is a token? Token can be anything which is between two spaces or between a space and a punctuation mark, which can be words or numbers, acronyms, word roots, any set of character strings between two spaces or a space and a punctuation mark. So if you take this is a token, this is a token, and is a token. Then type to token ratio. So basically types are the number of different words. Tokens doesn't, like each word in itself is a token. So type to token ratio basically gives you the ratio between the different types of words present and the total number of tokens within them. If you take the complete Shakespeare work, there are total of 884,647 word tokens, but only 29,066 word types, which translates to type to token ratio of 0.32032, which this basically says that if TTR scores are low, then we have the tendency to use the same words more in the conversation, and if it's high, tendency to use different words. Okay. Then the process of tokenization. Tokenization is basically splitting up big paragraphs into tokens or words, which we previously saw, string of tokens. You can even do sentence tokenization or word level tokenization, splitting it into either a sentence or a word respectively. So over here, you also need to know about bigrams, trigrams, n-grams. What are these terms? While tokenizing, you can tokenize just two words together, two consecutive words together. For example, this session is a bigram, just two words, two tokens. And trigrams, this session is an n-grams. This session is going to be 6 plus gram. So, okay, stopwords. Stopwords refers to most common words used in a language. We can essentially remove these stopwords to reduce noise from the data we have given. Because it's anyway, it does not have any segments in processing the language, so we can as well remove it. We are only focused on the nouns and verbs in particular. Then normalization is indexing text and query terms to have to match with the same form which is being represented differently. So if you take USA and USA where dots are there, and this word should be matched together and not as separate tokens. And then let's go into stemming. Stemming is a normalization technique where we reduce the inflected words. Inflected words meaning multiple words of a root, multiple forms of a root word into the word stem or the base root form. If you see these words, fishing, fished, and fisher, all of these are reduced to the stem word fish. Then if you look at argue, argued, argues, arguing, argus, stem word is argue. Eat, eaten, eating, stem word is eat. Like basically there are multiple algorithms such as Porter's algorithm, Lancaster's algorithm, which applies different methods. Porter's algorithm basically removes the s, ing, and orders proceeding. It removes and replaces well-known suffix of English words, as I said, ing and whatnot. The problem is stemming is if you take a word like ring, that will be, if you do apply stemming using Porter's algorithm on that, it will give just R as the result. Stem would be just R. It will remove the ing part. So that's one of the key drawbacks of stemming, where it just directly uses the algorithm, doesn't check for morphological or any actual meaningful word, if the stem is a meaningful word in the dictionary or not. Then there's lemmatization, which is again a way to reduce the token to its root form. So it's basically better than stemming and does the same serves the same purpose, but here we do morphological analysis and return only the meaningful word and proper form. So let's we'll have a small hands-on session on all these pre-processing techniques we have seen. We'll take a paragraph, we'll remove all the punctuation and all the unrelated symbols, which is basically cleaning part. Then we'll separate tokens from them. Then we'll apply stemming and lemmatization on them. So till here, do you guys have any doubts? Okay, I'm guessing there are no doubts, so we can proceed with the practical session. Mukesh, can you help me with the practical session? My collab is not connecting mobile data.
Okay. Okay. Should I share the screen and run as you tell?
Like, yeah, fine. That would be better actually.
I think there's a question he asked
Yeah.
for it.
Okay, so what's the difference between tokenization and lemmatization? Okay, in tokenization, you basically reduce, you take a paragraph and try to split it into tokens. Tokens can be anything. They don't need to be the root word. Like the word going over here is a token, but the root word of going is just go. If you take, if you consider fishing is a token, but lemmatization tries to convert that to its root word, fish. Basically, we try to remove all the redundancies. So if we find all these words in the paragraph, we try to map it to the root verb of fish. There's fishing, fished, fisher, all will be mapped to the root verb fish. This is stemming, same, both lemmatization and stemming converted to the root verb, but the main thing in lemmatization is that we get a meaningful root word. It doesn't blindly remove all the suffixes like in stemming. Stemming, we just try to remove Porter's algorithm on other algorithm, try to remove the ing, s, en parts of the word, and we try to get the root. But in words like over here also, the roots may not be proper in such cases. But in lemmatization, we only get roots which are present in the dictionary. So that again, we make sure using morphological analysis and we find the closest root word using other forms of distance measures like edit distance and whatnot between closest dictionary words and try to get that word as the root.
Akash, can you tell me where you have placed the notebook?
Okay, I think it's the same as the one in our docs, the first notebook on text processing. I think.
Is this the one?
Yeah, that's one only. So the yeah, first one just till the lemmatization part.
Yeah.
So
This one, right?
yeah, okay. And we try to have them do along with us. Like we also type along with them. Like we can share that window and finally share the notebook as well as we do.
Okay.
Like,
Can I share the notebook?
yeah, I can share it after this session. Maybe let them give it a try. They won't.
Okay.
Okay, first up, let's take any of the text. Go to any Wikipedia article or whatever article you feel, take a paragraph from that and assign it to a text string. So if you guys could follow along, like that will be great for you guys. Or you can also see what we are doing and then try to do it later. We'll anyway be sharing the notebook with you guys. So this is basically the pre-processing techniques. Like we are taking an input paragraph. It can be anything. Like you can take any articles, any paragraph from any articles which you find, and on that we first clean out all the punctuations like commas and all the unnecessary punctuations. Then we try to separate the tokens from them, find the word frequencies of each word, get the top 5 frequencies, then unable to see what's me. Okay, Mukesh, you are presenting, right?
Yeah.
Can you guys see Mukesh's screen? I'll guide you along as he runs each module and we'll give time to go through each module. Okay. Are you guys able to see the screen presented by Mukesh?
Yeah.
Oh, okay. Okay, it's visible, Mukesh. You can go ahead. Okay, first we have taken a paragraph into the text, and as you can see, the paragraph is being displayed. And now the length of text basically gives us how many characters are there in that, which we simply take for the sake. Mukesh, can you create a new cell below the length of text?
Yeah.
So before going further, we need to clean the data of all the punctuations and all the other unrelated stuff which we feel are not required. So we can do that either using setting a string with all the unnecessary words ourselves, or we can use a regular expression to remove whatever is other than spaces and words. So we'll be using regular expressions since it's much more efficient on larger data. Import array, then below that we put you can just one second. You can directly give result equal to re dot before
Lowercase it first.
okay. So what she's basically doing is giving in regular expression or colon opening brackets and the closing bracket, whatever we give within the brackets is what we need to include or exclude. Over here, yes, whatever is not of A to Z and numbers and space, he's replacing with empty characters. Okay, so since we are previously converted into lower now, and all the commas and all the exclamation marks and all the stuff other than word characters and spaces have been removed. So next up, we use the NLTK library over here. Basically, there are various libraries. We can either use NLTK or Spacey to accomplish the same results. NLTK library basically has all the algorithms to tokenize stem, to do parts, to tag parts of speech and all those things. So we first split the text based on all the spaces. We get individual tokens in the text now. Okay. Okay, this is not token. This is like basically what we have done. Now word tokenizer gives us the token basically. Download PUNKT punct before this. Can you run that on the clean text? Tokens is word tokenize of process text. Okay. So we get all the tokens which are present. Okay, now commas and all the expression marks, all the punctuations are gone. So yeah, now we get the tokens available for that paragraph. Now let's look at the frequency distribution. So each token can appear multiple number of times. So if we want to know the frequency of how many times it has occurred, we use frequency distribution, which is there in LLTK.probability. So if we give frequency distribution of token, we get frequency distribution as a dictionary for each token value pair. Then we can filter out the top 5 frequencies, frequent words, and all the other things which is required for language modeling. So if we want to get just the top 5 most frequent words being used in the para, you can give most common of 5. It will give you the top 5 words, most used words. Okay, now n-grams. Okay, we use text blob from the text blob library to basically find all the n-grams. You can n-grams is basically if n-grams n is 2, it's bigram, which means in the string we have India officially, the Republic. So India officially will be a bigram, the Republic will be a bigram, and all the consecutive words of size n will be put together and given us that number of grams. So text blob of our text.n-grams of 2 will give bigrams, n-grams of 3 will give trigrams, and so on and so forth. So now we have seen what stemming means, and we are importing Porter stemmer for our stemming. Porter stemmer algorithm basically removes all the suffixes using a set of rules present in the Porter stemming. So as you can see, the stems of the word sending is send, giving is give, formulae, plural is formula, knives is knife, and not knife. That's a problem we have with stemming, which is not. It gives you a root word, but it may or may not be a word present in the dictionary. So to avoid that, we use lemmatization. Stemming is still used because it's fastest, and you don't need to do any morphological analysis and get the closest word in the dictionary using distance measures. So lemmatization requires much more processing. So we still use stemming in many cases. Here we use WordNet lematizer to perform lemmatization. So yeah, over here, if we lemmatize the word knives, its root word is knife, which is a meaningful word present in the dictionary. Same way, stop words we have seen, all the common occurring words, the, is, whatnot, we can find all these stop words present in a string, and also we can remove the string to facilitate better processing. Stop words just add more noise to our data. So these are the stop words that's found in this string. On our clean text. Okay, it's fine. This text is also fine. The, of, is, and all those things have been removed from our text, as you can see. So this is the basic part of pre-processing the data before we even go into performing the basic tasks of NLP. In basic tasks of NLP, we try to disambiguize all the language related ambiguities and also extract information from the text. So over here, we'll see lots of parts of speech tagging, named entity recognition, dependency parsing, and all those things to better how to understand each sentence, get the context out of the sentence, and resolve all the ambiguities as well. So Mukesh will be taking over from this part. He will teach you all the basic tasks in NLP. So
yeah, okay, I'll share my screen.
yeah.
Okay. Okay. So is my screen visible?
Yeah, it is visible.
Yes.
Okay. So again, welcome to everyone. So Akash has spoken to us about what is natural language processing and how and why we need computers to be able to process, understand, and perform useful tasks upon the language that we are used to every day, our common mode of communication, which is the human language. Why we need computers to be able to understand that, and why is there a need for such a bridge of tools that can help computers understand our language, right? And he also talked about why deterministically understanding the meaning of a sentence in natural language is challenging because of the inherent ambiguities that are there in the language, and why there is a need for external world knowledge and the context of what is being spoken to truly understand the meaning of a sentence. So, and he also motivated us with a variety of examples that of NLP systems that are very evident. It can be something like Google Translate, which we are often used to, or it can be the spam filter that works in your Outlook or Gmail that you don't notice, but some mails that that work behind the scenes to let you not let with very high precision to let advertisements and other unrelated mails go into your spam folder. Or it can be other algorithms that work behind huge websites such as Twitter to analyze the sentiment of masses about what is being spoken about a subject. Or it can be as simple as something as a Google search. When you look for some question, you get the exact answer you were looking for. So he motivated us with a lot of such examples and lots and lots, such as Grammarly and editors on words which help correct our language, which serve as writing aiding tools. So since we have been motivated and we are now aware that NLP is ubiquitous and it is prevalent all around us, we need to understand how some of these tasks are built, how some of these systems are built, what are the basic tasks or building blocks that go into many of these systems. So we'll get started with some of the basic tasks or representative tasks in NLP. So I'll start off with a simple task which goes behind simple NLP, which is a very basic NLP task. So the task is called parts of speech tagging. So given a sentence, any sentence, let's assume the sentence, the dog is cute, right? So we need to identify what is the part of speech tag that is associated with each word, right? So whether it is a noun, whether it is a determiner, whether it's an adjective, or whether it's a punctuation, because this will help us down the line, right? So it can be used to perform more advanced tasks, right? Suppose I know that the noun is the one that is the most important thing in the sentence. So when I'm doing some tasks like summarization, I can use it. Or maybe let's say there is a sentence like, let's say bat is a nocturnal animal, and I like to bat in cricket. In one case, bat is a noun. In other case, bat is a verb. So to be able to understand what is being spoken in a sentence, we need to know what this part of speech tag associated with each sentence is. So once we know what parts of speech tagging is, we need to be able to we are curious about how we can build such systems, right? So let me say I have I want to build a parts of speech tagger for myself, although there are a lot publicly available. Let's suppose that we want to build a parts of speech tagger. How do I go about doing that? So if you want to build a stochastic or a probabilistic model, which basically uses statistics from the data set that we create. So we have a training corpus. So we have plenty of sentences that are taken from public sources such as Wikipedia or some books or somewhere, and let's say we use a team of human annotators to annotate the sentence with the parts of speech tag for each token or word. Let's say we create such a data set. How do we go about training a system that can emit the part of speech tag for each of these sentences? How do we go about that? So a simple approach is that we could just see that in my training data that I have created, what is the parts of speech tag that is most used for that given word. Let's say there is a new word that comes in, a new sentence that comes in. Let's say the sentence is that the cat is cute. So we see what is the parts of speech tag that is most commonly used in the training data set I have created what is the most common parts of speech tag for the. So the most common parts of speech tag for the is the determiner. So we assign the determinant POS tag to the. And similarly, we see what is used for the other words, and for majority of the words, we tend to get it right. Surprisingly, for English language, it so happens that on some data sets we are able to get as much as 91% of the token predictions correct. Although in certain cases, as we saw earlier, where the word can be used interchangeably as a verb and a noun, those cases we tend to miss for a small number of cases. So this is the simple approach I was talking about. So let's say I have a data set, I'm training a model or something that has to parts of speech tag a new sentence that I have not seen. So what I do is I assign the tag that is most commonly used for that particular word. Let's say I have the word heat. I would use it could either be a noun with a 94.7% probability. That is 94.7% of cases in my training data. It has been used as a noun, and only as 0.5% of the cases it has been used as a verb, right? So there is a heat transfer from A to B. That means heat is a noun. I'm going to heat something. It means heat is a verb, right? So if you do this kind of simple approach or stupid approach, we may call, if you want to call it, we still get a good accuracy for certain amount of cases, good number of cases, right? So this is a very simple approach, and the problem with this approach is very evident that we cannot tell whether when the word can be used interchangeably, we are stupidly assigning the most probable scenario or the most probable tag to that particular thing without looking at its context, right? So So a more broader approach or a more would be to basically so given an unseen sentence such as this, let's say I went to the market, I need to assign a set of tags T1, T2, T3, T4, and T5 to each of the words in this sentence. What I would do is that I have to go ahead and find a set of tags that are most probable for this given sentence using the training data set by drawing statistics from the training data set. And what we generally do is we tend to make uh, certain simplifications to this formula, probability of the tag set of sequence of tags for a given word, and we tend to identify that sequence of tags which is most probable for this sentence, right? So I think so this is a very simple task that could be used down the pipeline. So I think we can go ahead and since it's a very simple task, we can go ahead and try it on our own. So I think you would have got the link to the drive that I have pasted here, and I think I'll paste it once again now. So if you haven't seen it, I think I've pasted it once again, right? So what we can do is we can go ahead and try POS tagging a sentence. Let's say, let's start off with the okay. So I'll be using a library called Spacey for this, which is along with NLTK one of the most popular libraries in Python for NLP related applications, simple tasks. So this is the Spacey library that I will be using, and it is relatively simple to do parts of speech tagging using Spacey. So what I'm going to do is I'm going to first go ahead and I'm going to import the library called Spacey. I think you can follow along with me. There is I've sent a link, and in that you would find a folder called notebooks, and in that you would find something called POS tagging. And I think if you could open that with a collab, or if it asks you to make a copy, you can make a copy of it. Right. So yeah. Yeah. Any questions or anything? Okay, so I'll go ahead and import a model that is trained for English using data on the web, right? So it's a model that has been trained for a set of tasks for the English language using some resources on the web, right? So I'm going to just load that model, and I'm going to use that model to parse this sentence, right? So I'm going to create a document object out of it by using this model, right? And next, what I'm going to do is I'm going to traverse through all the tokens in the doc. So internally, this model has done a pipeline of steps, right? It has tokenized the sentence, it has identified sentence boundaries, and it has done POS tagging and other tasks. So what I'm going to do is I'm going to select the POS tag that is given to each of the words, right? So what I'm going to do is that I'm going to print the text of the token, in this case, welcome. And I'm going to print the simple POS tag, which is the standard set of POS tags or universal set of POS tags. And I'm going to ask it to explain what that POS tag means, right? So let me say I run it, right? So I see that welcome is a verb, to is an adposition, the is a determiner, workshop is a noun, on is an adposition, data is a proper noun, science is a proper noun, using is a verb, and is a proper noun, not punctuation, right? So I think this is you should be able to run this notebook. If you are having any issues, you can let me know. Okay. So this was something called as the universal set of stats. Yeah.
சார் அந்த மார்க் லிஸ்ட் பிரிண்ட் அவுட் எடுக்கணும்லங்க சார்? ஆமாங்க சார், அது 1 2 3 மூணுமே பிரிண்ட் அவுட் எடுக்கணுங்க சார். மூணுமே எக்ஸாம்ஸ்ல கொடுக்கணும். ஆனா என்னன்னா நம்ம எக்ஸாம் நடந்த ஆர்டர் இருக்குல்ல சார், அதே ஆர்டர்ல தான் மார்க் லிஸ்ட் இருக்கணும் சார். இப்ப நமக்கு பாத்தீங்கன்னா ஊப்ஸ் முன்னாடி இருக்கும், ஆனா ஊப்ஸ் கடைசி எக்ஸாம். சோ நம்ம ஃபார்ம்லயும் வந்து அந்த டேட் வைஸ் தான் இருக்கணும் சார்.
Ma'am, can you please mute
அது மட்டும்
yourself?
மாத்தணும் சார். சப்போஸ் கன்சாலிடேட் கொடுத்தீங்கன்னா நீங்க மாத்தி கொடுத்துருங்க சார்.
ஹலோ.
இல்ல அவங்க கொடுக்கலன்னாங்க சார். அவங்க 3rd இயருக்கு மட்டும் தான் வந்திருக்குன்னு அன்னைக்கு மீட்டிங்ல சொன்னாங்க. சரி 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 சரிங்க. ஆமா, மூணுமே வந்து நமக்கு இன்டர்னல் டைம் டேபிள்ல என்ன ஆர்டர் இருக்கோ அதே மாதிரி இருக்குங்க சார்.
ஓகே.
வாங்கிக்கலாம் சார். இதை நம்ம வேணா சொல்லிடலாங்க சார், இந்த மாதிரி ஆர்டர் மாத்தி போட்டோம் அதனால நாங்க மாத்திக்கிறோம் அப்படின்னு சொல்லிக்கலாம் சார். இப்ப நான் போட சொல்லிடுறேங்க சார். ஓகேங்க சார்.
Nidita, ma'am.
Can you mute your audio?
அக்கா சொல்லுங்க.
1 second, I'll contact.
Yeah. Okay. So I think this is called the universal POS tags, and the description for all of these universal POS tags can be found here. So you see that the description for adjective, what kinds of words are described as adjective, will be found here. Now let's go ahead and get a more detailed POS tags for each of these, which is more detailed than what we saw earlier as adverbs and adjectives. So I do the same thing. I traverse through each of the tokens. I print the text of the token. I print something called as the tag, which is the POS tag, and I ask Spacey to explain what this POS tag is. So you should be able to see that I get more detailed POS tagging, such as verb, non-third person, singular present, and things like punctuation mark, sentence closer, and more detailed POS tags. I think it was relatively. I think you should be able to follow along with this notebook. If anyone is having any issues, you can let me know. Okay. Okay. Shall I continue, or is there any problem? Okay. 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 Fine. Okay. I think I'll continue. I'll go on to the next task. Next, so we looked at the first basic task in NLP that makes up NLP systems. So another important task is a text classification, right? So to understand how we can use traditional machine learning methods, or how traditional machine learning works for text, so let us consider this bunch of food reviews, right? So our objective in this case would be to predict the star ratings that the customer could have given along with each of these reviews. So these reviews have been, let's assume that they have been taken from a food reviewing site, or a restaurant ordering sites such as Zomato, Swiggy, or related sites, and we have been given the text, but somehow we lost information of what the star rating that the person had given to the text. So we have been tasked with finding what the star rating for each of these texts would be, given that we have been given the input food reviews that we can use, right? So how do we go about solving this problem using NLP text classification techniques, right? So what we could do is that in traditional machine learning approaches, what we do is we kind of try to understand or identify features or indicators that could aid our task at hand, right? So we try to identify what could be helpful to predict the star rating from this text. What attributes could be helpful, right? For example, let me say that the presence of a word with a negative sentiment, like let's say awful or awful or horrible or worst could be an indicator that the review has a very poor rating. And let's say words with a positive sentiment, let's say such as I love the food or the food is great or delicious, could mean a very high rating, sentence with a very high rating, right? So what so happens is that a lot of machine learning methods tend to perform really well when the features or input representations are handcrafted, right? So let's look at what the handcrafted features could be in this case, right? So I could use something, I could extract a feature from this text. Is the word awful present in the review? Is it present or not, right? So is the word great not preceded by not present in the review? Because the word not great would mean that it is a bad review, but I just want to make sure the word not is there. Is it there? No, in this word, the word not is not present in this review, right? So what is the number of reviews? So maybe there is a thing, right? Long reviews tend to mean poor performance and complaints, right? So we include the number of words in the review as a feature. And we can say, is the word love this place present in the review, right? So we look and scan through a lot of such text documents, and we come up with a set of features that could be used to aid our task at hand, right? So there are similar such things like, is the word horrible present in the review? But it should be associated with either food or service. So we want to look whether the horrible is present within two distance of the word service, right? So it means the word horrible is related with service. If service is somewhere in the beginning and horrible is not associated with it, then this feature would not be fired, right? So we have used this technique to convert the text that a computer cannot understand to a set of features for the review. So we have been able to describe our text to the computer or the algorithm using a set of features, and this becomes the representation for the text for the learning algorithm, right? So now we have represented our data in the form of text we have converted that data into a tabular form that we all know and love, and we have been using to train and predict using the common machine learning algorithms that you might have seen in the session on supervised learning. I think Harini was talking about k-nearest neighbors and naive Bayes. So you could use those algorithms given training data in the form of features and true labels, which is 1 in this case, 3 in this case, right? So given set of features for each text and the target, you could such lot of such training examples in tabular form. You could use classifiers such as the k-nearest neighbor or naive Bayes or SVM or decision trees, any of the classifiers to basically train your models, right? So what we see is that there is limitations. So we see that this process consists of 2 steps, right? So the first step is describing your data with a set of features that the computer can understand, and the other step is using a learning algorithm or learning a function that approximate the mapping from the input features to the output target. So we use the training data to learn a function that can approximate the mapping from the input features to the output target, which is the star rating, right? So okay, so let's go ahead and look at, so what we have done now currently is we have used human curated features, handcrafted features to describe the text to my computer. Now, is there a more automated way of coming up with features from text? The problem with handcrafted features is that they tend to be over specific, or they tend to miss out on things. There is no huge coverage of various things that would be necessary for the task. So the question is there a better way, or is there a more automated way of doing this? Yes. So there is something called as a bag of words model, right? So the bag of words model says that each sentence or document can be expressed as a set of or bag of words, right? So let's say we are given documents that we want to convert to the bag of words feature. Let's say the sentence is the food was awful and service horrible, right? The same sentences. I love this place, right? So what you do is initially you come up with the list of all words in our vocabulary, right? You extract all the unique possible words from these set of documents, right? And we see that there are only 14 unique words since we are using only 3 documents. Then what we do is that we tend to use each of these vocabulary items, and, awful, decent, was, all these as a feature or a dimension of the feature vector that we are going to use to represent this sentence. So you can see that the sentence, the food was awful and the service horrible. You can see that the dimension corresponding to the feature the is 1, right? The dimension corresponding to food is 1, to was is 1, to awful is 1, and is 1, and is 1, the is 1, service is 1, and horrible is 1, right? So similarly, we describe each of the sentences by a vector of this form, which is consist of binary indicator variables. That is 1 if that word is present in the document, and it is 0 if the word is not present in the document, right? So this is the simplest scoring method you can use. You can also kind of slightly modify it to, instead of using the binary indicator variables that you see 1, you could use the frequency of the number of times the word occurs in that particular document, instead of just using a binary indicator variable. So this is how you convert a document to a bag of words features, right? Bag of words model. Okay, now there is a particular problem in the name itself, right? It's called a bag of words or a set of words, right? So the problem with this approach is that any information about the ordering of words is lost, right? Let's to understand that, let's consider these sentences. The food was great, not bad, right? And let's consider the second sentence. The food was bad, not great, right? These are completely contradicting sentences, but the set of words that have been used in both these sentences are just the same. And so you can see that the feature vectors that we have used to represent these sentences are just the same, right? So as far as the learning algorithm is concerned, these sentences are represented by the same representation, and therefore they mean the same to these learning algorithms, right? So this is a very it's a very fundamental problem with a bag of words. So the question arises, how can I improve this? How can I bring in the information about the ordering or the context in which the word is used in order to into the feature representation for that sentence, right? So it's a vector of numbers or binary values that I'm using to represent my sentence. How can I bring in the ordering information, right? So what we can do is that we can change the unit that we are using as dimensions or features, unit of text that we are using as dimensions or features in our feature vector, right? So we see that and has been translated into a feature, was has been translated into a feature, love it has been translated into a feature. So we can change this fundamental unit that we have, or the fundamental feature or dimension that we have used to represent the sentences, right? So that is where n-grams come in. So what you do is you take a sliding window and you essentially you slide the window through the text, right? Let's say I have this document. The food was great, not bad. So I slide the window and I get pairs of 2 words as my basic unit of text that I will use in my feature representation, right? So I have had a sliding window of 2 and I've got all these features or vocabulary items that I could use in my feature vector. Now, let me say I use a larger sliding window of 3. The food was good, not, and good, not bad, right? So these are of dimension 3. And similarly, I can go for sliding windows of size 4. Now the thing is that although the same set of words could be used in both the sentences, since we are using sliding windows, those 2 sentences would have different feature representations, right? So let me do one thing. Let me represent the second document also using the same set of features. Right now, you see that I have represented both the document using these features. So these are called n-grams, right? And if I use a sliding window of 2 to get them, these are called bigrams. And if I use a sliding window of 3 to get them, they're called trigrams. And if I use a sliding window of 4 to get them, they're called 4grams, right? So you see that although the same set of words have been used in both, I have used both unigrams and bigrams to represent my sentences. You can see that the feature representations are different, right? So it is because although the unigrams are same, the food was not good, not bad. You see that the food was, but if you see here, was good, was bad, and things like not bad is activated in one, whereas in other case not good is coming in another, right? So by using pairs or triplets of words as the basic vocabulary item instead of just individual words or unigrams, we can essentially bring in information about the ordering of words and about the context in which these words are used into the feature creation process, right? So I think I can give a small demo. So before I go into the demo of how you can convert a text to a vector and how you can fit a classifier to learn from these feature representations, is there any doubt on what I have covered of how to convert text to features using a bag of words model or n-grams model or anything on handcrafted features? Is there any doubt on these things? Am I audible?
Yes,
Yeah.
Mukesh.
Okay. Okay, so I think either people. Okay, I think I assume that there is no doubt, right? So let's get going. Okay, so in this case, what I'm going to do is I'm going to create a text classifier into which I give a text. It will be able to new text. It will be able to tell me from what class or category the given text came from, right? So okay, so this has been this tutorial uses scikit-learn. Right. So what we'll be doing in this data set, in this tutorial, is that if you want, you can follow along with me. Right. This is available in the drive link which I have given. You go to notebooks, and there is a notebook on text classification, which you can follow along with me. Right. So what I'm going to do is that I'm going to load the data set first. I'm going to convert each of the documents or text in the data set into bag of words or n-grams features, right? And I'm going to fit a classifier such as a naive-based classifier, which is a algorithm that learns to approximate the mapping from input to output, and you give it a new data point, it will be able to tell you what class it came from. So let's get started. So initially what I'm going to be doing is I'm going to be using a data set called a news groups data set, 20 news group data set. It is a publicly available data set, and it essentially takes a set of about 20,000 news articles. A news group is not exactly news articles, it's a set of articles that were kind of discussions on discussion forums such as Google or Quora or Stack Overflow, similar kind of discussion forums. Such kind of documents have been taken, and they are actually from 20 different categories. But what we will be using is only 4 different categories out of the 20 that are available, right? So we have categories on atheism, and we have category on religion, and we have category on graphics, computer graphics, and we have a category on medicine, right? So these are the set of categories that I will be using in my data set, right? So let me go ahead and define the categories as a list, right? Yeah, right. Right. And now what I'm going to do is I'm going to create, or I'm going to initialize the dataset object. I'm going to download the dataset and I'm going to initialize it in an object. So sklearn provides a set of toy datasets to us, and I'm going to be using the 20 news group, which is one among them. So let me go ahead and let me just import the function called as fetch 20 news group, right? And I'm going to just go ahead and import the function, and I'm going to download the dataset and I'm going to load it in this object called train dataset. So I am going to be first loading the train split of the dataset, and I'm going to be using these 4 categories that I have defined here, right? So let me go ahead and download my dataset. You can follow along with me. I think the notebook is available in the drive link, right? And you can stop me and ask if you have any queries, right? So let's see what is there in this dataset object that we have got, right? So in the dataset objects, we have something called as data, which is the set of documents. We have target names, so which you should be able to see is the set of classes or categories that these documents come from. So every document will come from one of these 4 categories, right? And we have something called as target, right? So mainly we are interested in these 3 items: data, target names, and target. So we'll be looking at what data stores and what target stores while we explore the data set. So let me go ahead and let me print an item in the data attribute, right? So this is a discussion about converting images to HP LaserJet 3. And does anyone know of a good way or standard application to convert TIFF image or TGA files into some format, right? So we know that this is a document from the category computer.graphics, because it could not be from the other categories, which is atheism, Christianity, and medicine, right? So this is the first zeroth document item from. So train.data is a list of items, right? Just show it to you. I think I shouldn't. Okay. So you can see that's a very huge list of around 2,000, 3,000 documents, where we have the text of the document, right? So it's a list of texts. So what I'm going to be doing next is let me see another document, right, from another category. Let me print the 9th document in the training dataset. So this is a document about blind sight, right? So explain, I thought there were 3 types of cones equivalent to RGB. And it's about color blindness, right? This is why the 2 most common kinds of color blindness are this and this, right? So it's a medicine about medicine and less about graphics, right? So
Yes,
what I'm going to be doing, yeah.
Mukesh Shivaselvan,
Yes, sir.
sorry for interrupting.
Yes.
One Dr. Meenakshi Mittal, madam, okay, right? I think he's asking, kindly repeat what is the purpose of adding categories. Huh?
Okay, so
kindly
yeah,
repeat what is the
sorry.
purpose of adding categories. Sorry for interrupting.
Yeah, sorry, I didn't see the
No,
message.
I understood. See, the teacher's eyes cannot revolve around 360 degrees. That is why I intervened.
Okay.
Thank you.
So this 20 news group data set has a collection of documents that come from 20 different categories. So, and I don't want to be using the whole pool of categories or classes while training my data set. So I'm going to be using only documents from 4 categories. Let's say in my case, I had star ratings, right? So these are the classes or categories. Star rating 1 is a class, star rating 3 is a class, star rating 5 is a class, right? So let's say that I decide to use only 3 star ratings and I decide to drop documents that are star rating 2 and 4. That's the same thing I'm doing here, right? So I just don't want to be using the documents from all 20 categories. So I am not sure where we'll find those categories list. It should be available on public datasets like UCI and others, 20 news group datasets, a very common dataset, and you should be able to see all the categories that are available in the dataset. So these are the 20 categories, right? There is about sports, there is about electronics. So I decide to use 4 categories from these, which are graphics, atheism, and medicine. So I use only 4 categories. So there are 20,000 documents and I'm using only a subset of them. That is why I define the categories, right? So I think it should be clear now. So now that we have seen what is in the data set, we have a text document and we have a label that is associated with the text document. Let's try to build a classifier into which if I give a document like this, it will be automatically able to tell me from which category it came from. So I'm giving an unknown document or an unseen document that the model has not seen before, and it should be able to throw out from which category it came from, right? So we know that classification is a supervised learning technique, which means that you need a sample to have a class or a target associated with it, right? So you have a data, you have an object, you have the class or category it belongs to. So you have multiple such objects and you have the class it belongs to, right? So let me see what are the classes that each of them belong to, right? So that is available in a attribute called dot target, and I'm printing the first 10 elements from that list. It's a NumPy array and I'm printing the first 10 elements, right? So and how do I interpret this? As I saw earlier, the target names corresponding to these indices are available in the thing called target names, right? So let me go ahead and print what these target names are and what indices and what do each of these numbers mean, right? So I just went ahead and I just put these 2 together, this one and this target together, and I can see that 0 is alt.atheism, 1 is computer.graphics, 2 is science.medicine, and 3 is religion.christian. Okay. So the next step is, since we have explored the data set, we know what is there in the data set, we have documents, we have categories. Let's go ahead and apply what we have learned, right? So let's go ahead and extract bag of words features from each of these text. And right, so we need to first convert text into numerical features, or we need to convert them into bag of words features, right? So what I'm going to do is that I'm going to be using something called as a count vectorizer, and count vectorizer nicely packages all the pre-processing, the tokenization, stop words removals, and other things that you have to do on the text, and the things that you need to do to convert it to a bag of words feature, right? So I'm just going to going to import count vectorizer, which can be used to extract bag of words feature from text. And I'm just going to go ahead and I'm going to just import it from feature extraction.text from sklearn or scikit-learn, right? And I don't want to complicate things, so I keep the default parameters and I go with them. Okay. So I have already shown you what is there in dataset.data. So it is a list of documents. So I want to convert each of these documents to a bag of words feature. So the method that I would be using is something called as a fit_transform. First, what it will do is it will first go ahead and extract the list of all possible words that are there in this and use each of the words as a dimension for the feature, right? So okay, so I think here it is. So I'm going to go ahead and I'm converted the train dataset documents, which is train dataset.data, into train dataset_x, which is a array of dimension 2257 cross 35,778. So the number of documents, right? So let me say number of documents. Okay, number of documents is equal to train _dataset_x dot shape of 0, right? And let me go ahead and say number of features or number of feature dimensions, right? It's train dataset_x dot shape of 1, right? So there are about 35,788 possible feature dimensions or words that we have extracted from the dataset. And since we would be curious about to know what those words are, I'm going to print those, right? I'm going to just do count vectorizer dot vocabulary. So it says that the word at index 29724 is simple, right? And 3249 is thing, right? So we have a feature that is 35,788 such feature dimensions for each document, right? And I am just printed it as a list, right? I have done is that I have printed the 0th index, the first index feature word, second index feature word, and I have done it for all the documents, and we would have 35,000, which is a long list of features. So we can't be looking at all of them, right? So we can see that I have created bag of words features from the 2,257 documents in the train dataset, right? And which is train _dataset_x. These are the bag of words features, and I have already printed shape, right? Now let me print what is there in this array, right? Although it seems like a matrix of all zeros, actually there are certain positions where it is 1. So let me see. Let me just go ahead to 0 and let me say np.where. Let me just import np as numpy as np, and let me say np.where this is not equal to 0, right? And I'm just going to say I'm going to just print it. So it's going to tell me that for the first document, or I'm just taking the first row, which corresponds to the first document. It says that there are about 73 elements which are not 0. Let me go ahead and see which are those indices, right? np.where, okay, 0 not equal to 0. Okay, just giving me an error. Let's see. There's a better. What is the problem? I'm not aware of this. Okay. Let me do one thing. Yeah, let me do 2 array. Yeah. So it says that the elements at indices 177, 230. These indices are non-zero elements, and if you were to see, I think I had printed a vocabulary somewhere earlier. So yeah, feature words list of what these indices are, 177. You should be able to see what these features mean, right? Okay, I'm having an issue. Okay.
Yes, I'm sorry.
Yeah. Yes,
Okay, Shivaselvan, sorry to interrupt again.
yeah. It's fine.
Any indication of what time more required?
How long it will take?
Yeah, correct. That's what I'm asking. So that I think it's already 1:30, right? How long maximum will you need?
Okay, 10 minutes should it be fine?
Okay. Okay. By 1:45 wind up, right? So that at least they get a 45-minute break. Okay.
Okay.
And
Okay.
whatever is left over, you can push it to the afternoon lab session. Okay.
Okay. Yeah.
Don't rush through whatever you tell it properly. Something is getting missed out, you can always cover it in the lab session. Okay.
Okay. Yeah.
Sorry. Okay. Sorry.
Yeah. Okay. Okay. So I think we'll continue for another 10 minutes or 15 minutes at most, and we'll break for lunch. So okay. So I was saying that okay. So these are the indices which are non-zero, right? So we had an array, we converted each document to a feature vector. There are some ones and lots of zeros. That is why you see it like this, right? I'm not sure. Let's just check it out. What the issue is. Okay, so that word was 071. There are a lot of such words. You should be able to see what you could see what those words are, right? And finally, what we have done now is that we have for each document we have a bag of words feature, and we have a class label that is available in the variable target, right? Right. So the bag of words feature for the first document is available here, and the class category 1, which is associated, the category which is associated with that one is available in target. Right. So now that we have our document as features and as categories, right? Feature category pairs, we should be able to train a classifier, right? So let me go ahead and let me train a multinomial name-based classifier, right? Which is a learning algorithm, right? So what this classifier would be able to do once trained is that we would be given a new document, we would be able to predict from what category that came from, right? So let me go ahead and let me import multinomial name base from the scikit-learn library, right? And let me just go ahead and create the classifier object with the default parameters. Let me not change anything, right? Okay, so let me go ahead and use the fit function of the classifier. So I'm going to go ahead and I'm going to give the bag of words feature corresponding to each data, and I'm going to go ahead and I'm going to give the target values that are associated with each data, and I'm telling please learn a mapping from the bag of words feature for each document to the target value for each document, right? So I've just went ahead and I have asked the model to learn the parameters from this data set, so that when I give a new document, you are in a position to be able to predict from which category it came from. Right? Now let me go ahead and let me just have fitted my classifier. I have a trained classifier. Let me just go and play around with it and see from which category a document would have come from. Right? Let me just define a list of documents, which is OpenGL on the GPU's fast, and I know that it comes from something like the graphics class, right? So I go ahead and convert this document, toy document. Let's just simply call it the toy documents list, right? And I'm going to just convert it into a bag of words feature using the same count vectorizer that I had used earlier. It's important to note that we have to use the same count vectorizer object that we had used earlier, because we want to convert these documents also using the same method or using the same feature dimensions that we did earlier, right? So I'm going to just go ahead and I'm just going to convert it to bag of words features. And we see that there is only one document and it has the same number of 35,788 dimensions. And let me just go ahead and see what is it is an array. It is also a bag of bits feature, which although seems like a lot of zeros, has certain dimensions as 1, right? So let me go ahead and use my trained classifier to predict for this toy data set, toy document, right? I go ahead and I ask it to predict, and it says the class category for this is 1, and I should be able to see from a trained data set dot target names that category is essentially computer.graphics at the first position, right? And let me just go ahead and print it. So I'm saying that OpenGL on the GPU is fast belongs to computer.graphics. So you should be able to play around with it. You should be able to put in some maybe something like color blindness, and you should be able to get a different results, right? I think it should say it's a document from okay, I think there is a
blindness spelling is wrong.
what?
Blindness spelling.
Okay. Maybe we are
Excellent. Very good, sir. Very good.
So I think there is some issue. I think we can. I think it's not. There is certain issue. I think we can just skip over this part, and we can essentially go test it on a larger data set, right? So I'm going to be using a test data set, which also comes as part of the 20 use group data set. I'm just going to use the test documents, and I'm going to test it on the test documents, because I cannot say how good the classifier is by just looking at one particular document, right? I have to test it across a bunch of documents. So let me just go ahead and let me just go ahead and see what is there in the first document. Test dataset.data of 0. So this is some help for some kidney stones. So it is, as I recall from my something, there is a kidney stone and stuff. So it is a document from science.medicine, right? Now let me convert the documents in test dataset into bag of words features, right? So let me use the same count vectorizer that I have used to fit on my trained dataset, and let me convert it to a bag of words features, each of the document, right? And you can see that it is 1502 documents in the test set is available, and each of the documents have the same 35788 features, in which each dimension is already the same word that we defined for our train set, right? The count vectorizer created a vocabulary from the train set of 3578 documents. The same set of documents are being available here as well, right? So let me go ahead, since I have test data underscore x, right, which is the bag of words feature for each and I have a test dataset dot target, which is, I know that I'm not going to be using the target in this case, but I'm just going to be using it to see how good my classifier has performed, right? So I'm going to do classifier dot predict test dataset underscore features, which is test dataset underscore x, and I get the predicted labels for these 1502 documents, right? So let me go ahead and let me see what my model has predicted for the first document, right? So I got the predicted classes using classifier.predict, and I'm going to be using that, right? I'm just going to see what is the first element in that predicted list. And I see that the first element in that predicted list is science.medicine. So my classifier has rightly identified that this document with the model, it was not there in the training set, belongs to a science.medicine category, right? So let me see another example like that. So this is some random article on, I think, atheism or something. So many of the atheists posting here argue against their own parody of religion, blah, blah, blah. And so what it has predicted 0, right? So I'm just seeing what is the third item. I'm just seeing it says it's atheism. So we see that for the examples we have manually seen, it is performing quite good. And finally, we want to see across all the documents how many has it got right. For the 2 documents I have seen it has got right. For across all the 1502 documents in my trainings test set, how many has it got right? So these are the true labels, which is test dataset.target, and which has 1502 items. Test dataset predicted classes array is the list of classes predicted by my dataset, and let me use something called as a classification report, right? Which will generate all the classification metrics that might have been spoken about earlier: precision, recall, accuracy, and other metrics which are task specific, right? So I'm going to just, what I'm going to do is I'm going to give it the set of true labels, which is test dataset.target. And I'm going to give it the set of predicted labels, which is test dataset predicted class array. And I'm going to tell that the names of the classes for indices, index 2 is this thing, index 0 is this thing. I'm just going to give that list, and I'm just creating the classification report. Okay, go ahead and run this. Okay. Yeah. Now you see the classification report. So let's concentrate on this thing here, which is called as the accuracy, right? So accuracy is the number of items in the test set for which the model was able to predict the class correctly, right? So let's say that I have an accuracy of 0.9341, which means that out of the 1502 documents in my test set, 93.41% was corrected predictably. So what is 93.41% of 1502? Let me just do that, right? 90.9341 of 1502, right? So that is 1403, which means out of 1502 documents, 1403 documents I was able to get correctly, and only 100 documents I failed, right? And we were able to do this using only simple bag of words approach, where I didn't even use a bigram or trigrams. I used only a unigrams, right? By default, it uses only unigrams unless you explicitly specify it to use bigrams and trigrams, right? So let me see for how many it has got correct. Let me just calculate it. Just see. And as I have said, I have got it for 1403 items correctly, right? I predicted that 1403 items should be correct because the accuracy was 0.9341, and we have got it correctly for 1403 items. Yeah. So I think we have covered what is POS tagging and what is text classification. So I think post lunch we would be looking at another way of converting text to features, which would be TF-IDF, and followed by which we will be having some demos and materials on how to extract information from text, and certain other tasks or hot topics in NLP. We would just touch up on some of those topics, such as document summarization, among others. Yeah. Yeah, I think we can break for lunch. Yeah. If you have any doubts or have any concerns, you can raise. Am I audible?
Yeah, you're audible.
Yeah. So I think we can break for lunch. When should we be back? Okay, I think Harini will be taking the session after this, right? For an hour?
Yeah, correct.
Okay. Yeah. Okay. Yeah, thank you.
So we can have a break, and again, afternoon session will be starting by 2:30.
Okay. Should we share any doc where they can ask doubts like we did the first day? Or?
No, but here they were like able to chat on chat here itself, right? So
okay.
Okay, later if they have any doubt, we will consult it. Yeah, we will send them.
Okay. If any of you have any doubts, please feel free to ask. Okay. Thank you.